One of the next things that we can do is apply some information about water and calculate some energies that are associated with the phase changes that water can undergo. And that's where we introduce this concept called the molar enthalpy of fusion. Now, I'm probably going to anticipate that you're feeling a little overwhelmed maybe with this language, but really, once you break these parts down, it doesn't seem so bad. First of all, let's talk about what the word fusion refers to, right? It's enthalpy of fusion. So the word fusion really refers to things fusing together, coming together, and that's actually the process that might conjure up images of particles that might be flowing about freely like a liquid, and then fusing together to form a solid. And that's in fact what it's really referring to. So the word fusion, again, that's basically some glorified scientific word, at least in this context, for the process of freezing. The word enthalpy, now this is new, and this is something that we'll talk some more about in just a minute, so I'm going to skip over that, but I do want to talk about the word molar. And the word molar refers to, of course, relating to mole amounts, right? So we have some way to talk about amounts, but again, it could be in grams, it could be in volumes, but in this case, we're talking about specifically mole amounts. And then finally, the one I've been skipping over is enthalpy. Now, enthalpy is a brand new term. Enthalpy really refers to the amount of energy, which, somewhat familiar to you guys, but it's about the energy per mole. It's about an energy change per mole affiliated with some phase change. So you can see here in the definition, it's the amount of energy released to freeze 1 mole of a solid, right? So it frees 1 mole into a solid anyway. And a couple of symbols here. First of all, this delta H right here, this delta H, the actual meaning of delta and H, well, delta refers to change, but H, that's actually the symbol for enthalpy for what it's worth. Why H and the word enthalpy is involved, I'm not really sure. But just know that enthalpy, again, refers to delta H. And then the FUS, F-U-S right there, F-U-S, that's actually referring to fusion. So really, delta H is referring to enthalpy, and then the fact that you're talking about a fusion process has the little notation of FUS, fusion. The units here are in kilojoules per mole, kJ, right? K for the kilo, K-I-L-O, and then joules, you probably remember that from a long time ago when we discussed energy, but that's kilojoules as in 1,000 joules per 1 mole. So we can say that per mole of substance, there's going to be some amount of kilojoules of energy that is either released or absorbed. For water, the delta H of fusion is 6.009 kilojoules per mole. Now, what this basically tells us is that we can say that if we're given any amount of water, we can figure out how much energy is absorbed or released. So in this question, you see in this example one at the bottom anyway, how much energy is released when 0.788 moles of water freezes? Provide your answer in kilojoules. Well, thankfully, it's really not too bad because in this case, we just have the mole amount given to us. So I know it's 0.788 moles of water. And it's being frozen, right? So is there a way that we can relate the amount in moles and the energy associated with it? Absolutely. We have the delta H of fusion, right? We have this kilojoule per mole amount that we can apply. And so we're going to set it up like this because we're going to have 6.009 kilojoules of energy released per 1 mole of water that is frozen. So this step right here, this entire thing, right, this is basically the conversion factor that relates this, right? That is your same value, and that represents the delta H of fusion for water. Right, and of course, you can plug these numbers into your calculator and do a little bit of math, and you'll find that the answer here is 4.74 kilojoules of energy. Now again, let's put some context into this problem, right? So what we're saying is that what happened here is that this amount of water, whatever it is, this amount of water froze. And in order for something to freeze, it has to give off energy, right? So to give off energy, as the process occurs, it's going to freeze your sample into some ice. So it takes 4.74 kilojoules of energy to be released. Now, again, what are we talking about when it comes to energy, right? Remember, we're thinking about the little particles moving around, right? All the individual particles that might have some water molecules anyway, might have some energy associated with it, right? And then what we're doing is we're slowing it down to where they will freeze. And this is the amount of energy it takes to freeze that 0.788 moles of water. Let's try this again. But in this case, this language of fusion is also potentially confusing, and it's a little, in my mind, and to me anyway, a little bit obnoxious, but the word fusion sounds like it's only applying to the freezing process, but it actually applies to the melting process too, because what do we know about the freezing process? Well, it's basically the opposite of the melting process. And so when we talk about the word fusion, the word really applies to both the freezing and the melting processes, just that they're in opposite directions. We still use the same value. So in this example, let's go ahead and take a look at this one. How many kilojoules of energy is required to melt a 10-gram sample of water at 0 degrees Celsius? All right, well, let's go and break this one down. Well, first of all, we are given this idea that it is going to be a melting process that I underlined here. And so even though, right, this is not really the same thing as fusion, right? Fusion, of course, is about freezing things together. It still uses the same value, the same delta H. Now, let's make sure we're clear about this, right? The delta H of fusion, which we're just going to steal from the previous page, that's going to be 6.009 kilojoules per mole. So that's still relevant here. That hasn't changed. And all we're going to do now is we're basically going to apply this problem now, or at least apply this delta H fusion to this problem. So in this case, we're going to be melting 10 grams of water. So 10.00 grams of water. And of course, that's now not an appropriate value. We can just stick the delta H of fusion because, again, as a gram amount, we can't apply a kilojoules per mole amount. So we have to convert that into moles first. So you can see the molar mass of water. You can add that up on your own, but speed things along. Go ahead and give it the molar mass there, 18.02. And then we know that for every 1 mole of H2O, you're going to then have to require 6.009 kilojoules of energy to melt it. Right? And that's basically what this is saying. So this delta H of fusion, again, this whole term can be applied in this part right here. Right? This whole term is going to be applied in this section. And then at this point, you basically do some math. The only thing that's different about this problem, again, is that we used a gram amount to start with, but that's something that you can easily convert into moles. And more importantly, the idea is that even though it's talking about melting, right, we still use the same value as if it's the delta H of fusion, which sounds like we're actually going to cause it to freeze, right, because those processes are opposites. Anyway, you plug these numbers in, solve for some math, you get 3.33 kilojoules of energy that's necessary to melt 10 grams of water. So you're putting in this kinetic energy so that the particles will disrupt those IMFs and then become a liquid. As you can see here, right, if we have fusion, then we also have this other part, which is, in this case, a molar enthalpy of vaporization. Now, this one, hopefully, at least on the surface, sounds a lot more familiar, because vaporization, I think we can kind of visualize what that looks like, and we're familiar with that term. And so the breakdown is more or less the same. It's the amount of energy required to vaporize 1 mole of a liquid, right? So taking a liquid and changing it into its vapor form, into a gas. Notice some similarities here. The symbol, delta H, is showing up again, right? Delta H refers to the enthalpy. And then VAP, V-A-P, right? That's referring to vaporization. So delta H of VAP. And then, of course, the units are kilojoules a mole, just like before, because this is molar enthalpy, right? Kilojoules per mole amount of this substance that's present. More often than not, of course, we'll be working with water, so the delta H of VAP is going to be 40.79 kilojoules per mole. So, in this language, right, a sample of water required 119 kilojoules of energy to completely boil at 100 degrees Celsius. How many moles of water were in the sample to start with? All right, so we're given energy this time. It doesn't seem like we're given the same amount as last time. We're not just given some gram amount or mole amount. This time we're given an energy amount, and they're asked for how much water there was. Well, again, kind of thinking about this going backwards, if I'm given an energy amount, 119 kilojoules of energy, that's going to then be kind of compared here, since we're talking about the fact that we're boiling, we use the delta H of vape. We're going to compare that to that amount. So we go ahead and stick in that it's 40.79 kilojoules of energy for every 1 mole of water that is boiled. And the setup basically, again, is saying that I know how much energy it took. How much water then would it have been able to boil away? In this case, you do a little bit of math here, and you get 2.92 moles of water that was boiled. So we know that 119 kilojoules of energy can boil away 2.92 moles of water. And in case you're wondering, that's about a 1/4 cup of water or so. Now again, the same idea as before, when we have this term vaporization, that sounds like it's only talking about taking a sample from a liquid to a gas, but as we mentioned before, the opposite process is also just as acceptable. So going from the gaseous phase down to the liquid phase, you also use the same value, just kind of thinking about this going in the opposite direction. So let's see how this problem is going to work out. How many kilojoules of energy is released when 10-gram sample of water vapor is changed to a liquid, right? So we're going now from a liquid changing from a gas to a liquid phase, kind of going what sounds like the opposite of vaporization, and yet we still use that same value. So let's put this together. 10.0 grams of agua. And we know that since the gram amount of water can't be applied to the enthalpy of vaporization, we have to convert that into mole amounts. So once again, using that same molar mass as always for water. And now we have a mole amount, so then we just basically apply whatever kilojoules of per mole it requires for something to vaporize, which is the same energy per mole as it would take to condense. And that would be, for every 1 mole of H2O that is condensed, 40.79 kilojoules of energy is going to be released. Because again, going from gas to liquid, we're losing some energy, making it a little bit cooler, or at least in the process of making the particles move a little slower, and so energy is released, and that's effectively how you set up. It's the same value as if it were vaporizing, but it's, in this case we're talking about condensing. Now, to finish it out, you do some math, plug some numbers in, so on and so forth. You should be getting 22.6 kilojoules of energy released for this to be converted back into a liquid. To kind of wrap it up here, let's think about this for a second. We have some comparisons I want to go over. All the examples we had just gone over have really been about water, but water is not the only substance that can change phases, right? That makes sense. Multiple things can go from liquid to a gas, gas to a liquid, solid to a liquid, so on and so forth. And yet, we look at the value here for water, for example. The delta H of fusion is 6.009 kilojoules per mole. The delta H of vaporization is 40.79 kilojoules per mole. So the question is, why is the value for vaporization so much higher than for fusion, right? So if I did have 1 mole of water, and I took it through the vaporization process, versus if I had 1 mole of water and took it through the fusion process, why is the vaporization value so much higher? Now let's kind of think of it this way, and this to kind of keep things reasonably standard, at least in terms of comparison. Remember that fusion, right, is going from a solid to a liquid, and also liquid to a solid. But we're just going to go in the direction of warming it up, because I think we generally tend to think of things better that way. So going from a solid to a liquid, things warm up, and the particles kind of are disrupted in certain ways. And whereas from a liquid to a gas, right, it takes some energy, of course, to disrupt the liquid particles to become a gas. So why is the value for vaporization that much higher? Well, remember, in order to disrupt to change the phase from a solid to a liquid, you're changing and disrupting the IMFs, right? So you're really disrupting only some of the intermolecular forces attractions as you go from a solid to a liquid. Because when something's a liquid, there are still a decent amount of intermolecular forces present, even though the particles are moving faster, even though the kinetic energy is higher. And so you only disrupt partially, anyway, the IMFs when you go from a solid to a liquid. However, when it goes from a liquid to a gas, what is a gas's intermolecular attractions like compared to the liquid? Well, the gases have a lot less intermolecular attractions. The particles are bouncing around all over the place. They're not even attracted to each other in any seemingly obvious fashion. So it turns out that we actually don't have IMFs, or at least the IMFs aren't able to exert any real attractions. And so the delta H of vaporization is much higher, because instead of just partially disrupting IMFs, like you see here with the delta H of fusion, we're actually going to completely disrupt the IMF so that there's not even really having an effect at all. And that takes a lot more energy to completely vaporize a sample from a liquid than it takes for something to melt. In another comparison, we also have methane. So I'm asking you again to just collectively look at the delta H of fusion for methane and the delta H of vaporization, and then compare that to the same values, the corresponding values for the water, right? So why is this value compared to this one? Why is the fusion values for methane and the vaporization value for methane so much lower than the corresponding ones for water? So let's also think about that too, right? Well, what do we know about methane and water? Well, they're obviously two different substances, but what does that tell you about the IMFs? Tell me about that. So in order to disrupt, again, something going from a solid to a liquid, you have a lot less energy required to be put in, which means that the IMFs for methane are going to be a lot weaker. At the same time, for vaporization, this process going from a liquid to a gas, same idea, right? If you have a much less energy required to disrupt them, to change it from a solid liquid to a gas, that means you also have much weaker intermolecular attractions holding them into place. Therefore, not as much energy is required to be put in. Here's some practice problems, really just two, kind of giving you some work to try these out on your own. And make sure you read the questions carefully. If you haven't done so, make sure that you do set these up appropriately, and making sure that you follow the significant figures. And then finally, to wrap this up, other observations of water in this entire set, of course, is discussing water. Water is a really important substance, and you've heard of this plenty. And some of the things that you might consider is that water, despite how slippery and wet we usually view it as, it's also kind of sticky as a very strong glue, but not in the sense that we can use it to join two things, and like as if it were glue. It's actually one of those things where if you set water between two really flat planes of glass, for example, or flat panes of glass, you can say that too, it takes an immense amount of force to separate them. You can't really just pull them apart. For whatever reason, water has a really strong intermolecular force that keeps two things really close together. And finally here, water is ubiquitous, right? Meaning it's everywhere. And then also it's very reactive at the same time. And so much of what we have done as humanity over the generations, from ancient times up to now, really has to deal with water. So not only do we need to get sources of water, we also have to clean it, don't we? We also have to make sure that it is going to be safe to consume and use. And also, we have to avoid moisture buildup in homes, businesses, structures on a daily basis. We don't want mold to grow and have things get soggy and get destroyed that way. We also need to prevent rust on these very important ships and bridges and docks. These ships, of course, are really important because a lot of the stuff we buy comes from overseas that gets shipped over the water. Bridges, we drive across them every day, and water is going to be constantly brushing up against it. So we got to know how to handle that appropriately. Same thing with docks, right, with shipping. It's also important that we design the flow of rainwater so that our cities are safe. Right? When we have lots of times where there's a ton of water that comes down around us, and if we didn't have proper planning for drainage, then we'd have a lot more destruction and a lot more general just bad things going on if that water isn't taken care of. And then, of course, you want to make sure that water flow goes through our pipes and goes through our plumbing safely. You want to make sure that we do have good, clean water that we can consume. This same idea with water goes into agriculture, manufacturing, all sorts of other parts of our lives that we don't necessarily interact with on a daily basis, but we definitely have to consider how water plays into it. Okay, that'll do it.